Okay, we will start with trig function, right triangle approach. Now, suppose I have a right triangle. Now I don't like this right triangle. Suppose we have a right triangle and the angle of the one of the acute angle, let me call that theta. Okay, now let's say we have this right triangle with angle theta. Then here's the definition. Sine of theta is defined to be the opposite over hypotenuse. So if this is angle theta here, then the opposite will be this side. Okay, this is the opposite. Now, of course, the hypotenuse always the longest side of that right triangle. Okay, and the adjacent of angle theta is here. Okay. This is the hypotenuse. Sine theta is the opposite of the hypotenuse. Cosine theta is the adjacent over the hypotenuse. And then tangent theta is defined to be the opposite over the adjacent. Now, this group, sine, cosine, theta, I usually call that the primary trig function. Okay, something you have to memorize by heart. Okay, let me name it. This is the primary trig function. And then the secondary one, we are secant. Now, secant theta is the reciprocal of cosine theta. You can memorize it that way. But of course, if you see the formula for cosine is adjacent over hypotenuse. Now, secant is the reciprocal of that. That will be then the hypotenuse over the adjacent. Now, cosecant theta is 1 over sine, the reciprocal of sine. So once you memorize the formula for sine, which is opposite over hypotenuse, then the formula for cosecant will be the reciprocal of that. Cotangent is the reciprocal of tangent. Which is the adjacent over opposite. Okay, now this is the secondary trig functions. Now, there are a couple reasons why I separate trig function, the primary and the secondary functions, because the primary trig functions, especially because that when we need to do trigonometry, most of the discussion actually on sine, cosine, tangent. Okay, most of the discussion is actually on sine, cosine, tangent. That's one. Another reason is when you look at your calculator has sine, cosine, tangent functions. They don't have secant, cosecant, cotangent. But again, the reason our calculator don't have secant, cosecant, cotangent is mainly because even in the theoretical approach, at our level right now, we actually focus on sine, cosine, tangent. Okay, now using this definition, let's take a look on some example. I hope that these examples are actually quite simple. Example 1. Now, suppose I have a right triangle. Suppose I have a right triangle. Let's say this is triangle ABC, right angle at C. Okay. Now, the naming of our triangle, if named after the vertices, then the opposite side of that angle is denoted by lowercase. Okay, so let's say this is vertex A, then the side opposite to that vertex is written using lowercase of the vertex. So this will be side B. The hypotenuse will be side C. Okay, now, well, anyway, don't worry about that for now. That's something you're supposed to have learned in geometry though. Now, suppose I have, this is 4 and this is 3 by Pythagorean theorem. By Pythagorean theorem, then you will see that the hypotenuse is 5. Now, that's something we all have known. Okay, now suppose I ask you what is sine A? What is the value of sine A? Sine A is defined to be the opposite of angle A, that's 3, over the hypotenuse. While cosine A is defined to be the adjacent of angle A over the hypotenuse. And tangent A is defined to be the opposite over the adjacent. Okay. Now, secant, cosecant, and cotangent are the reciprocal of these three. Now, for example, secant A is the reciprocal of cosine. Okay, secant A is the reciprocal of cosine. That will be 5 over 4. And cosecant of A is the reciprocal of sine. That will be, the value will be 5 over 3. Now, cotangent of A is the reciprocal of tangent. Will be, that's the reciprocal of tangent. So the value will be 4 over 3. Okay, I wonder if I'm too fast. This part here is, I believe, is supposed to be very, very easy. But at the same time, I need you to be really good at that. It's to the point that this is something I would like you to memorize right away. Okay, I cannot even wait until Wednesday. Okay, right away. Now, using the same triangle, then let me ask you to do what happens if the point of view is angle B. So I would like you to compute or find the value of sine B, cosine B, and tangent B. Just write them in fraction, okay? And then after that, secant B, cosecant B, and cotangent B. Let me give you 2 minutes for this. So if the point of view is B, angle B, then the opposite will be 4, and the hypotenuse is 5. For cosine B, that's the adjacent, which is 3 over hypotenuse 5. tangent B is opposite over adjacent. Now, secant, honestly, if you ask me what is the definition of secant, I don't remember. I just remember that secant is the reciprocal of cosine. So at the back of my mind, if you ask me what's the value of secant B, then at the back of my mind, I compute cosine B first, and then I do the reciprocal. Okay, that's how I do it. But of course, you find your own style. Okay, sine B is reciprocal, or cosecant B is the reciprocal of sine B. That's 5/4. And then cotangent B is reciprocal of tangent B. That's 3/4. Okay. Now, some little note may be useful for us in future. There is something called Pythagorean triplets. Pythagorean triplet. Now that's defined to be the following. If this set A, B, C is a triplet, Pythagorean triplets, if they satisfy Pythagorean theorem, A squared plus B squared equals C squared. Of course, the assumption is C is the longest side. Okay. In fact, if three numbers satisfy, if three numbers is a Pythagorean triplets, then they can be the sides of a right triangle. Now, some examples of Pythagorean triplets, the one we have seen, that's 3, 4, 5, is one of them. Okay, another well-known one is 5, 12, 13. Okay, and then 7, 24, 25. And another one is, I think is 8, 15, 17. Okay, I actually list them in the order of how often they show up. 3, 4, 5 is the most often one. Okay, and then 5, 12, 13, 7, 24, 25, 8, 15, 17. Now, so if you see, for example, right triangle as the following, if you have this right triangle, and then for example, you see the hypotenuse is 25, and the other leg is 24. Then if you memorize that triplet, then you realize, oh, you know what? The hypotenuse is 25, okay? And one of the leg is 24, then the other leg must be 7. Okay, that's how we use it. Instead of like keep on using Pythagorean theorem again and again and again for something we do very often anyway, we will just do it by memorizing. Okay, so in your test, suppose I give you a triangle, okay, a right triangle that satisfies Pythagorean triplets, you can just use this triplet value. Like the one I showed you earlier, if you see the hypotenuse is 25, one of the leg is 24, you don't need to show me the computation how you get that 7. Okay, but only if it is a triplet. If it is not a triplet, you need to show me. Okay, now another reason why I want you to memorize this triplet is because any multiple of Pythagorean triplet is a triplet. Now, for example, we have seen up there that 5, 12, 13 is a triplet. Okay, now because 5, 12, 13 is a triplet, then the multiple of that will also be a triplet. Now you can try. You will see that this triplet satisfies Pythagorean theorem. Okay, suppose I multiply by 4, for example, then you will see that 20, 48, 52 also a triplet. In fact, even if you divide, let's say I divide by 10, which is actually the same to multiply by 1 over 10, okay, then 0 0.5, 1.2, 1.3 is also a triplet, okay? Now, so knowing that it is a triplet, we can do the computation a lot faster. Now, coming back here, suppose I change this triangle here, I make it 2.5 and 2.4. Now, guess what? What is the other side? Then the other side must be 0.7. Okay? Now, the nice thing about trigonometry, and this is the reason we learn trigonometry. Now, suppose I want to find what is sine theta. Now, sine theta is the ratio of, in a right triangle, sine theta is the ratio of opposite over hypotenuse. Okay, so in this case, that will be 0.7 over 2.5, which if I multiply the top and the bottom by 10, I get 7 over 25. Right? Notice that the ratio sine theta that gives us the ratio of opposite over hypotenuse will be the same even if you multiply this by 10 or divide by 10. Okay, so trigonometry, one of the main purpose of trigonometry is seeing that once we have a fixed angle here, then the ratio of the opposite over hypotenuse or any ratio of these three sides here will be constant, however you enlarge or make it smaller. So suppose for example, I do it this way. Yeah, like let's say I cut it into half. So you will see the length here is 0.35, right? But if the length there is 0.35 using similar triangle, this will be 1.25. Right? If I divide this by 2, now that 2.5 will be divided by 2 also, right? But notice that 0.35 over 1.25, when I simplify, I will get the same value there. Okay, so that's again is the reason we learn Pythagorean theorem and relate that to trigonometry, right triangle, and to fasten, to speed up our computation. So some nice numbers, Pythagorean triplet will be, should be memorized. Now go on further. In fact, I would like you to do this one. The following is not Pythagorean triplet, even though it seems like it is, but no, it's not. The following is not a Pythagorean triplet. Suppose I use uh, 3 and 5 here. Okay, and then let's say this is the angle X. Now, I want you to first find the value of the hypotenuse. No, this is not 3, 4, 5. Okay, the hypotenuse should be longer. Okay, now this is not 3, 4, 5. Now, once you find that the hypotenuse, then you can find the value of sine X, cosine X, and tangent X. Okay, now simplify your value later on. But when I say simplify, doesn't mean you make it into decimal. No, it will be under some kind of square root, right? Okay, now if you can simplify, please do so. Okay, let me give you 1 minute from here. Let's see. This hypotenuse here will be square root of 3 squared plus 5 squared. I think that will be square root of 34. Unfortunately, I cannot simplify that further. That's the simplest in form of radical. So sine X will be 5 over radical 34. Cosine x will be 3 over radical 34. And tangent x will be 5 over 3. Now, as you know, it is a custom. If we have radical on the denominator, we simplify that. Okay? We multiply by radical 34, the top and the bottom. So we see something like this. Okay, let's go a bit further. So, in fact, we can do the following question. Suppose they say, let theta be an acute angle. What does it mean if it is an acute angle? So one thing we can do is we can put this theta in a right triangle. Okay, we can put the theta in a right triangle. Let's see, suppose we have the theta here. That's an acute angle, right? And let's say cosine theta equals to 12 over 13. Now, the question is find sine theta and then tangent theta. And of course, from there you can also find secant, cosecant, and cotangent. But let's just find these two first. Now, once we know that theta is an acute angle, which means we can put it in a right triangle, okay, then you can use this idea that cosine is adjacent over hypotenuse, right? So this is the hypotenuse. This is the adjacent of theta. That's 12 here, 13 here. Then by Pythagorean triplet, what will this be? 5. That will be 5, that's right. Okay, so sine theta will then be 5 over 13, and tangent theta will be 5 over 12. Okay, now once you get the sine, cosine, tangent, of course you can do the reciprocal for each one of them to get secant, cosecant, and cotangent. Okay, now instead of, I mean, this kind of question is way too easy for you, but let me change the question a little bit. Let me call that example 4a instead of example 5, or example 4b. I change it to be like this. You try to do it. Let theta be an acute angle. And tangent theta equals to x. You can see that x as x over 1. Now, what you will do is draw the right triangle. Okay, well, because the theta is an acute angle, right? So draw the right triangle. Okay, this is theta. Now then apply that ratio x over 1. This is x, this is 1. Let me give you some time to compute what is the hypotenuse, and then use the result to find sine theta and cosine theta. Okay, now we see that by Pythagorean theorem, this will be square root of 1 squared plus x squared. Therefore, sine theta will be the opposite of theta is x over the hypotenuse square root of 1 plus x squared. If you rationalize the denominator, this will be x square root of 1 plus x squared over 1 plus x squared. At this point, I need to say this first. At this point, sometimes you wonder, Thomas, do we always have to rationalize the denominator, like what you did in example 4 and just now? This is the rule of thumb. You're supposed to rationalize all denominator, okay? But sometimes when I do the grading, I try to be reasonable, okay? Sometimes I'll just let you go if you don't rationalize the denominator. Under what situation you don't need to rationalize? When I say you don't need to rationalize, okay? Okay, so if I don't say that you don't need to rationalize, then you rationalize anyway. Okay, so the default is rationalize the denominator until I told you you don't need to do so. Okay, that's for you. When I do my grading, do I want you to rationalize the denominator? It's up to me. But for you, if you don't know, just do it. Okay, going extra mile when you show your work, never wrong. Okay, what's wrong is when you don't do enough. Okay, coming back here. So what is cosine theta? That will be 1 over square root of 1 plus x squared, which is square root of 1 plus x squared over 1 plus x squared. Okay, now that's if we know that tangent theta is equal to x and theta is an acute angle. Now, example 4 is the type of question that you see in lower level trigonometry, let's say, when you take trigonometry class. But once you get to precalculus, the type of question you encounter should be something like example 4b. Okay, now let's go on. The next topic is on special triangles. Something that you need to memorize. Special angles, (30 degrees, 60 degrees, 45 degrees. I will first talk about the 45 degrees one because that's the easiest. 45 degrees case. The question is, what is the value of sine 45 degrees, cosine 45 degrees, and tangent 45 degrees? Something you have to memorize by Wednesday. Okay, you have to memorize this by Wednesday. Now, how do we get that? We start from a square. Oops, sorry. We start from a square. At which, well, we know because it is a square, then the angle, each of the angle is a right angle, right? Then what I do is I bisect that square diagonally. I bisect that square diagonally. Because I dissect that square diagonally, then what happened is the angle here becomes 45 degrees, right? In fact, it forms a isosceles right triangle. Isosceles right triangle is a triangle which is isosceles, means it has two congruent legs and a right angle. Okay, now suppose the sides of this triangle, are both A's here, A here, A here, A here. Then by Pythagorean theorem, you will see the hypotenuse, the diagonal of this square is A square root of 2. Now, let me take that triangle. Let me take this triangle here out. Okay, let me take it out so that we can focus on that right triangle. You will see that, you will notice that since the legs are congruent, okay, then this is A, then this is A square root of 2. Okay, so the legs has to be congruent, and the hypotenuse will be multiply the leg by square root of 2. Okay, another way to look at that is look at the ratio. If this is 1, then this must also be 1, and this must be square root of 2. Okay, if this is, let's say, 7, then this must be 7, then this must be 7 square root of 2. Okay. From the leg to the hypotenuse, multiply by square root of 2. From the hypotenuse going back to the leg, you divide by square root of 2. So kind of like a side note here. Let me put a side note here. Suppose this is 45 degrees, and you know this is 3, then this must be 3 radical 2. Okay? If you know one of the leg, then the hypotenuse multiplied by radical 2. On the other hand, if you know the hypotenuse instead, let's say the hypotenuse is, let's say 8, right? Don't forget that the context now is 45, 45, 90 degree triangle. Okay, isosceles right triangle. Now, if you have an isosceles right triangle and the hypotenuse is 8, then to go to the leg, you divide by radical 2. Notice that when I come from, if I come from the leg, going to the hypotenuse, I multiply by radical 2. If I come from the hypotenuse going to the leg, I divide by radical 2. Okay, now, but let's focus on the sine, cosine, tangent. Going back to that picture here, what is sine 45 degrees? Sine 45 degrees. You can use A's, you can use 7, but I will use the 1. Okay, I will use the 1. I will use this guy here. I will use the 1s. Now then, if I use the 1s, then sine 45 degree will be the opposite over hypotenuse. Rationalize the denominator. Then sine 45 degree is that value. In fact, you will see cosine 45 degrees also the same value, because it is, I mean, it will be adjacent over hypotenuse, but the adjacent are the same to the adjacent for sine. So it should give us the same value too. While tangent 45 degrees is 1 over 1, which is just 1. Okay, now I need you to memorize this. The earlier you memorize this, the better you are. Okay, the earlier you memorize this, the better you are. Okay, how to use this? We use that later on. Okay, we use that later on. Okay, in fact, since you have calculator, then you should be fine. But for some special angles like 45 degrees, 30 degrees, 60 degrees, I need you to give me the exact value. Okay, now the second one, the 30 degrees, and you will see at the same time we will get for 60 degrees sine 30 degrees, cosine 30 degrees, and tangent 30 degrees. How do we get the values? Now, the way we get the values for those sine, cosine, tangent of 30 degrees comes from equilateral triangle. Comes from equilateral triangle. Now, the idea is once I have equilateral triangle, oops, sorry. Once I have an equilateral triangle, I will do angle bisection. Now you notice that because it is equilateral triangle, then the angle, each of the angles are 60 degrees, right? Okay, even the top here also 60 degrees. Now, but because I bisect that, then this guy will be 30 degrees. And of course, this will be a right angle here. Now, suppose the length of this part, only this part, if I call this 1, if I call that 1, then what's the length here? Now notice the length here must be the same to the length here, right? Because again, it is an equilateral triangle. Okay, if this is 1, then
so
this guy is 2, and therefore this guy will be 2 as well. Okay, now let's focus on this right triangle here. I will pick it out. I will pick it out, and let's see that here. Now notice that we have this ratio now. If this is 60 degrees and 30 degrees, this is 1, this is twice of that, then by Pythagorean theorem, you will see this is radical 3. Okay, now think of this as the ratio. Okay, think of this as the ratio. If this is A, let me use another color. If this side is A, then this side must be 2A, and this side must be A radical 3. Okay, so from this guy, multiply by 2 to get that. Multiply by radical 3, get that. Okay, you will see in 30-60 degrees right triangle, then the ratio of the shortest side to the longest side is 1/2. Okay, so this is your stepping stone, multiply by 2, you get that. The hypotenuse, multiply by radical 3, you get the adjacent. Now, use that triangle to find this value. What's the value of sine 30 degrees, cosine 30 degrees, and tangent 30 degrees? Likewise, I would like you to also do, we have 60 degrees right triangle there. Okay, so you can actually use the same triangle to find sine 60 degrees, cosine 60 degrees, and tangent 60 degrees. Okay, now let me give you 2 minutes for that. No, 1 minute. Okay, sine 30 degree is 1/2. Cosine 30 degrees radical 3 over 2. While tangent 30 degree is 1 over radical 3, which becomes radical 3 over 3. Okay, 30 degrees here in this triangle. So the opposite is 1, the hypotenuse is 2, the adjacent is radical 3. Okay, while for 60 degrees, the sine will be sine 60 degrees is radical 3 over 2. Cosine 60 degree is 1/2. And tangent 60 degree is radical 3 over 1, which is just radical 3. Okay, now this is another important special angles trig functions that you have to memorize. Okay, you have to memorize. Because of this remote teaching, I cannot really give you a quiz, like in-class quiz, quote unquote. Okay, and even if I give you take-home quiz, you can just cheat from the notes. So if you ask me, do you really have to memorize this time? Do I have to memorize these timers for my quiz? No. How about for my test? Well, you will get slowed down so much, slow down, such that you won't be able to finish your test if you can't even memorize this. Okay, so you have to memorize this to be successful, not only in my class, but also in your calculus. Okay, of course, the aim is calculus, right? Not only passing this class. This is a teacher speaking from his heart. Please take it this way. We are all in this situation together. Like, I have to stay at home. I cannot go to school. You can't too. Okay. And when I give you, when I do the class, I understand some students, if you notice, that we have only 12 students attending this lecture right now. Okay, actually 11 students attending this lecture. There are 13 people here. Okay, one me and the other one are SI leader, right? Okay, so only 11 people really attending this class. While we're supposed to have originally around 30, right after after they tell us to do remote teaching. But at this point, I have only 11 or 18 students left in this class. Most students actually drop because they cannot handle remote learning, and I can understand that. Now, I also have some students already dropped and some students not dropping yet in the situation where, because their children have to stay home, they cannot really attend the lecture, okay? And because they need to take care of their children at home, right? And that's why I record this lecture so that they can watch it in other time, okay? But with that consideration that I have some students not able to attend my lecture synchronously with the class time, then I don't think it is appropriate and I don't think it's wise for me to give a quote-unquote in-class quiz, okay, even though it's remote, okay? So no, I'm not doing that. I'm not doing that. The most I can really suggest you is like, okay, you know what? Look at my old test, this one, and try to do it on your own. Look at the time, so on and so forth. Okay. Now, even with your test, I have found 3 students in my other class at West LA College actually cheating from each other. Too bad they cheat from wrong person, so they get really, really bad score anyway. But to be honest with you, even if you actually get somebody else to help you in your test, I cannot do that much. But I know one thing, you can pass this class without ever passing Calculus 1 in your life. Okay, why? Because if you pass this class without the, without the foundation that you need from this class, if you pass this class and you go to Calculus 1, let's say, okay, and trust me, you will struggle in calculus 1. Now, once you struggle, very likely what happened, now, of course, you need to repeat it, right? Now, how many times can you repeat it? Only 3 times until you move to another district. Now, what happened if you say, you know what, Thomas, I repent. I'm in calculus 1. I didn't do well in my precalculus, but I cheated such that I passed the class. Now I'm in calc 1. I want to repeat my precalculus. The answer is no. You cannot. The state law does not allow you to repeat the class that you already passed. Okay, so it's up to you. If you want to do that kind of thing, you know what? It will catch you eventually. Okay, so the way I see is, instead of relying too much of, you know what, let's care about that later, make your foundation stronger. Okay, and for trigonometry part, one of the things that you have to memorize is these 2 yellow boxes here. Okay, please, you need this. The later you memorize this, the slower you will be successful in trigonometry part. Okay, now let's summarize the trig value for these 3 special angles. I will make it like this. Okay, now for sine, cosine, and tangent of 30 degrees, 45 degrees, and 60 degrees. Okay, so 30 degrees, the sine is 1/2, cosine is radical 3/2. The tangent is 1/radical 3, which is radical 3/3. For 45 degrees, the sine of 45 degrees is 1/radical 2, which rationalized to be radical 2/2. For cosine, it is the same. For tangent is 1. For 60 degrees, the sine is radical 3/2. Cosine 60 degrees is 1/2. Tangent 60 degrees is radical 3. Okay, now please memorize this. Okay, in fact, I want to say memorize by Wednesday. Okay, what you can do to help you to memorize, try to copy this this table here maybe 3 or 4 times. Okay, 3 or 4 times in your flashcard, or you know what, even a regular paper is okay. And then you cut it and then stick it to next to your, let's say next to your bed, and stick one in your restroom maybe. Okay, now in the past I recommend some of my students to stick it on their dashboard. Okay, because very likely when you go to Santa Monica in the morning you hit some traffic, right? But right now you don't drive a lot, so I guess it's not necessary. Okay, but try to be creative in how to create your flashcards and put it in some places that you visit a lot. And while you sit down doing nothing but doing number 2, I'm sorry for being nasty here, but come on, man. Instead of using your cell phone during your restroom time, okay, you can just look at this and then try to memorize it. Okay, yeah. Now to help you to memorize, it will be much better if you take a look on how I derive the value. Okay, so remember this isosceles triangle, no, not isosceles, equilateral triangle that we bisect, and a square that we bisect. Okay, yeah, and it helps you a lot in memorizing them. It's really about how to memorize them and put them in your subconscious though. The faster, the better. Okay, now that's for the sine, cosine, tangent of 30, 45, and 60 degrees triangle. Now, how about the application? the application that I will do here, not only for these special angles, but angles in general. Okay, angles in general, the one we did earlier. But let's do the special triangle one first. Suppose, for example, so I call that example application 1. Suppose I have a ladder lean toward a wall. Let's say this is my ladder here. Let's say this is my ladder here. Okay, and then I know I know that the angle formed here is 60 degrees, let's say. Now suppose when I measure from the base of the wall to the base of the ladder, suppose this is 5 feet. Then the question is how high on the wall that this ladder reach. Okay, let's call that x. Let's call this x. So the question is, what will x be? Okay, now of course,
x be 10.
Actually no. You will see the ladder, the length of the ladder will be 10, but the x is okay. Let's see. By knowing this x, plus imagine if you set up here, okay, then you can kind of imagine, you know what? If I need to reach something on this wall, I can add maybe x feet plus 1 or 2 feet on the top of that. Okay, was for me to be able to be safe in reaching that item. Okay, but let's find that x first. Now, what relates this x and 5 and 60 degrees? What function, what trig function relates those?
Tangent.
Tangent. So that's the question. What trig function relates that's 5 feet, 60 degrees, and the x? Okay, and you are right. The relation will be tangent. Tangent 60 degrees is equal to x over 5, right? Does it make sense? Now, at the same time, by memorization, we know tangent 60 degrees is radical 3. Now, so x is equals to 5 radical 3 feet. Okay. Now, let's see application 2. This time, I would like you to look at your book. Application 2. Look at your book on page 347, number 24. The peak of Mount Fuji in Japan is approximately 12,400 feet high. So let's say I have the mount is here, like that. Okay. Now the height is 12,400 feet. A trigonometry student several miles away notes that the angle between level ground and the peak is 30 degrees. So suppose you standing as far as here, you stand here and you look at the peak of that Mount Fuji, okay, and realize the angle here is 30 degrees. The question is estimate the distance from the student to the point on the level ground directly beneath the peak. Okay, so the one in question is this. Okay, now that's the sketch, right? Now, which if we think about it, it's basically answering this question. Oops, sorry. It's basically answering this question. If this is 12,400 and this is 30 degrees, what will this be? Okay, that's basically the question. Okay, now let me ask you to take maybe 1 minute to answer that question. Okay, let's see what relates that 12,400 and x and 30 degrees. There will be, oh, again, it's tangent. Okay, tangent 30 degrees equals to 12,400 over x. Now, I understand some of you may say, oh, Thomas, why don't we use cotangent? You can use cotangent. Now, the thing is, there are two reasons why we don't use cotangent 30 degrees. When we learn our special angles, the 30, 45, 60 degrees angles, we didn't really talk about the cotangent, right? Okay, even though we can easily find it. But why do we want to work so hard doing cotangent while we have tangent in front of us, right? Okay, that's one. The second reason, and I think this is more important reason, is because even if we use calculator later on, take a look on your calculator does not have secant, cosecant, cotangent functions. No, you only have sine, cosine, and tangent. Is it right? Okay, so even if you want to use calculator later on, it will be kind of on the hard side to do it, okay? Tangent 30 degrees is 1 over radical 3, or you can also use radical 3 over 3 if you like. This is 12,400 over x. When I do cross multiply, I get x equals to 12,400 radical 3 feet. Okay, now that's how we get that. Now, suppose I modified that question a little bit. So let me call that number 24 modified. Suppose I change the angle theta instead to be, let's say, 27 degrees instead. Now notice that this 27 degrees is not a special angle. Then we need to use calculator. Okay, now not the special angle, so I need to use calculator. That will be tangent 27 degrees equals to 12,400 over x. So x times tangent 27 degrees equals to 12,400. Okay, and then x equals to 12,400 over tangent 27 degrees. Now, let me ask you to use your calculator to compute this with one hint. When you use your calculator, I assume that scientific calculator, the way you punch this on your calculator will be, you punch that 12,400 first, and then divide it by tangent 27. Okay, now I want you to use your calculator and see what's the result. I get x equals to 24,336.37027 feet. Just like before, round your answer to 5 decimal places. The thing is, if you get answer different from this, you need to let me know right away, because it has something to do with the way your calculator being set up. Okay, make sure you use your calculator and check. Now, I assume you use scientific calculator. I have graphing calculator, but I will just use the scientific part with us right now. Now, let's take a look. The way you punch it will be 12,400 divided by tangent 27. Thomas, why you get different answer than what you wrote earlier?
Are you in Radian mode?
That's right. Now, your calculator by default should be in degree mode, okay? But I use this TI-84 here together with my Calculus 2 class. So in your Calc 2 later on, you will see a lot of trigonometry, okay? There's no way in 1,000 years you can pass Calculus 2 without knowing how to do the part here, okay? Now, that I teach you today. Now, but why, Thomas, you get different answer? Because I am dealing with, let me press the mode here. So if you use TI-30, there must be a mode also there, okay? Now, when I press the mode, you see that I'm in Radian mode. And you see that I'm in Radian mode, okay? While my work supposed to be in degree mode, okay? So how do I get to degree mode on my calculator? I move to that row and go to degree and press enter. Now it is in degree mode. Okay, so I go back to that. I continue the entry, the same entry. Okay, and then I press enter. You see, I get the better answer right now. Okay, so I type in exactly the same expression, but because earlier the mode for the angle is in radian, then it will see that as a radian. Okay, right now I change the mode into degrees, then I get different answer. Okay, now if you use TI-30, let me see if I can put a TI-30 picture for you. Give me a second. Anybody use anything else besides TI-32, 32XS, or anything else? Okay, let me use this one here. Give me a second. Let's go back to our node. Are you on my note right now? Do you see this calculator?
Yeah, you see it.
Yeah, we see it.
Okay. Now, if you want to see which mode you are working on, then you need to type this. You need to type this. That's how you see the mode. Okay. Now then, when you type the mode, then it will tell you. I think. Let me see. A second. When you type mode, what do you see, by the way? I mean, I don't have that calculator with me.
It comes up with, it's kind of similar to the other one. It says
Oh, okay.
degree, radian, and then GRAD. I don't know what that stands for.
That's the grade. They call it the grade or gradient. Yeah, but what we worry here is only the degree mode and the radian mode. Okay. Now, every time you deal with an angle, pay attention if it uses degree mode, degree sign. Okay. This has degree sign. In the angle, the one here does not have degree sign. Okay, so going back, basically, I somehow think this way. If your calculator is new, if you bought it new, then by default, the manufacturer will set the default angle to degree. So you should get this answer directly earlier. Okay, but just in case you get it from somebody else, you buy it used or you borrow from somebody else, and very likely that person already changed it to radian mode, which we will learn in 5.1. Okay, yeah, but for now, using the degree mode, this is what it's supposed to look like. And if you are not in degree mode, change it. Okay, now right now it's 10:48. Let's take a little break. We come back at 11 o'clock. And at 11 o'clock, we will do some basic identities that you need to memorize further. And then we go back to 5.1. Okay, see you at 11 o'clock. The last part of this section, which is also as important as what I have mentioned earlier, are basic identities. And I need you to memorize these basic identities in addition to the trig values of those special angles. Now, we will have a lot of formulas when it comes to trigonometry part, and I will bombard you with some basic identities first. You have 2 days to memorize this. Okay, don't worry, it's not too hard. It's not too hard. The formulas here are actually quite short. I will break it into 3 groups for now. The first group, so I will call that D1 later on for basic identity. The first group is ratio and reciprocal identities. Ratio and reciprocal, which we basically already seen by definition earlier. That is that secant theta equals to 1 over cosine theta. Cosecant theta is 1 over sine theta. And cotangent theta is 1 over tangent theta. while tangent theta is basically sine theta over cosine theta. Okay, I think there's nothing to prove here, because these three here is basically definition, and the one we have here, you see that tangent theta supposed to be opposite over adjacent. Okay, but if I divide the top and the bottom by hypotenuse, then I get what I need, which is the sine theta over cosine theta. Okay, now that's for the ratio and reciprocal identity. The second identity is called Pythagorean identity. And you need to memorize it in this order. The first one, sine squared theta plus cosine squared theta equals to 1. Second, tangent squared theta plus 1 equals to secant squared theta. And the third one, 1 plus cotangent squared theta equals to cosecant squared theta. Okay, now when it comes to identities, when I say you need to memorize these formulas, and if I number it this way, 1, 2, 3, it means I need you to memorize it in that order. Okay, I need to memorize it in that order. Here's the thing, fast forward. In the next 1 or 2 weeks, you will see a lot of formulas, a total of at least 30. Okay, at least 30 identities. Now, the thing is, like, when we use those identities, instead of quoting the formula, in future, I will just quote the name or the group or the numbering. So, for example, if I want to quote this formula in future, I will just say B22. Okay, that's the address, that's the location, that's the formula. Okay, instead of writing this formula in full, I would just call it B22. Okay, so that's why I need you to memorize in that order also. But you will see the reason I put the numbering and require you to memorize in that order, it has something to do with the fact that, for example, B22 here, that formula actually coming from B21. Okay, and B23 is actually coming from B21 also. Okay, it also has something to do with the proving. Now let's do the proving. Proof. The proof B21. Okay, now the proof will be as the following. Notice that sine squared theta plus cosine squared theta is equal to opposite over hypotenuse squared plus adjacent over hypotenuse squared. Right? You will see that I actually prove it from left hand side. And then on the top I get opposite squared over hypotenuse squared plus adjacent squared over hypotenuse squared. I put them together in this common denominator. Hypotenuse squared at the bottom. On the top, I get opposite squared plus adjacent squared. Now, what is opposite squared plus adjacent squared? By Pythagorean theorem, that is hypotenuse squared on the top, right? But hypotenuse squared over hypotenuse squared, that's equals to 1. That's our right-hand side. That's what we try to do. Okay, now the proof that I show you here is a special case in which the angle theta is an acute angle. But you will see this formula actually applies in general, even when the theta is not an acute angle. Okay, now how about proving B22? B22, that is tangent squared theta plus 1 equals to secant squared theta. The proof will be as the following. We take the equation, the identity from B to 1, that is sine squared theta plus cosine squared theta equals to 1. Okay, and then I will divide that by cosine squared theta. Now, therefore, the first term we will have sine squared theta over cosine squared theta, plus the second term I get cosine squared theta over cosine squared theta. You see that guy will later on becomes 1. And then the last term is 1 over cosine squared theta. Now, what will this guy be?
Tangent squared theta.
That's tangent squared theta plus 1 equals to secant squared theta. Okay. That's the end of the proof. That's what we try to do. Right? Okay. Furthermore, how about B23? Proof B23. That is 1 plus cotangent squared theta equals to cosecant squared theta. The proof is very similar. We start from B to 1. And I want you to do this one. You copy down B to 1, and then instead of dividing by cosine squared, you will divide by sine squared theta. Okay, now try to mimic what we have there, up there. I give you 1 minute, or maybe 1.5. From B to 1, we get sine squared theta plus cosine squared theta equals to 1. Then we will divide by sine squared theta. So I get sine squared theta over sine squared theta plus cosine squared theta over sine squared theta equals to 1 over sine squared theta. The first term becomes 1. The second term becomes cotangent squared theta. The last term becomes cosecant squared theta. Okay. Now, the third group, group 3, is cofunction formula. And it comes from the word co that has something to do with what we call complementary angle before. Now, to help us with our intuition, let's take a look on this triangle here. We did this before. We did this before implicitly, but now I just try to make it explicit. Now, suppose this is angle A and this is angle B. Notice that A and B are complementary. In other words, A plus B equals to 90 degrees. Right? Now then, if two angles add up to 90 degrees, then they have this relationship that sine A equals to cosine B. Okay. The proof is actually quite simple. So let's say this is A, because this is vertex A, so this is side A, right? This is B, and this is the hypotenuse, let's call that C. Now sine A is A over C, right? Sine A is A over C, but at the same time you see that A over C from B point of view, angle B point of view, that's A over C also, okay? Sine A equals to A over C, but that A over C is cosine B. Okay. I hope you can see that, right? That's a little proof. Okay, now this is the first one. The second one is tangent. Tangent A is equal to cotangent B, and secant A equals to cosecant B. And the proof is actually visible from that triangle. Okay. Now, another way to write these formulas, is the following. Sine theta equals to cosine of the complementary angle. As long as these two angles add up to 90 degrees, as long as these two angles are complementary, then they are related by cofunctions. Okay, sine and cosine. Okay, tangent and cotangent, secant and cosecant. Okay, again, as long as those two angles add up to 90 degrees, then the cofunctions are equal. Actually, if you look back, if we look back up there, if we look back up here, notice that, for example, sine 30 degrees is the same to cosine 60 degrees. Right? 30 and 60, they add up to 90. So sine 30 equals to cosine 60. In fact, going further, sine 60 equals to cosine 30. Do you notice that? Right? And sine 45, the complementary angle of 45 degrees is 45 degrees. So sine 45 degrees is equal to cosine 45 degrees. Right? Let's write it down here as a note. Note that sine 30 degrees equals to cosine 60 degrees, vice versa. So sine 60 degrees equals to cosine 30 degrees, and sine 45 degrees equals to cosine 45 degrees. That's something we saw before, but we can say it even further. Let's say if I have sine 20 degrees, that equals to cosine what? That's right, 70 degrees. Okay, now tangent of 35 degrees will be equals to cotangent 55 degrees. Okay, so from this section, beside doing the suggested homework later on, what do I need you to memorize? I need you to memorize trig values or special angles, and B1, B2, B3. Okay, now of course earlier I also mentioned about Pythagorean triplets. Memorize this as early as possible. Okay, if you don't memorize it this Wednesday, then it will take you longer time to actually catch up with me. I promise you that one. Okay, I say this for you, not I say this because of my arrogance. I have my arrogance. Okay, trust me, I'm worse than Trump. I'm sorry, but you need this. Okay, you need this. Yeah, the better you memorize this, the earlier you memorize that, the better you are in catching up with me, in doing well in this class, and of course in doing well in your calculus class later on. Okay, now we have learned at this point we have approached trigonometry from a right triangle. Now this is a big approach in introducing trigonometry to new students. Okay, so I assume you never took a trig class, even though that's actually part of your geometry class, right? Okay, now, but the issue with right triangle approach, the weakness of this approach is we dealt with acute angle only. Acute angles only. Well, because if you think about it, once you have a right triangle, then you have one right angle. Well, it's a right triangle, so one of the angle must be right. But that also means the remaining 90 degrees, the total is 180, right? The total angles of the interior angles is 180 degrees. Okay, now that then if one of them is 90 degrees, then the other two must also be only add up to 90 degrees. Now it implies that the other two angles that we deal with here has to be acute angle. Okay, so the angle here and angle here has to be acute. No way out. Okay, so consequently, angle A and angle B are acute angle. Okay, we will try to extend the idea of trigonometry instead of only right triangle. Okay, now I'm not saying that this approach is bad. In fact, every time I teach trigonometry, since the very beginning of my career, I always start from right triangle. Okay, that's the simplest way to see trigonometry first. Okay, now then, once we see, oh, you know what, right triangle has its weakness, then how to overcome that weakness? How to then extend this idea later on to obtuse angles or even more than 180 degrees angles. Now then we will introduce a new point of view. Suppose I have a rectangular coordinate system, okay, and we have an angle in standard position. Now, I hope you still remember an angle in standard position. Oops. From positive x-axis to the terminal side with vertex at origin. Okay, now let's define coordinate P be x comma y. Okay, so let P be coordinate x comma y, and OP, the segment OP, is the terminal side of theta in standard position. Okay, now then we will define the following. Notice that if I pull this line down here, it forms a right triangle, okay, such that the length here is, according to that coordinate P x, y, this will be x, and this will be y. Okay, now borrowing the idea from a right triangle approach, we will define the following. Sine theta equals to x over r, where the r is the hypotenuse, where the r is the direct distance from A to P, O to P. Cosine theta equals to, I'm sorry, I think I write it wrong. Sine theta is y over r. Cosine theta is x over r. And tangent theta equals to y over x. Now notice that this definition here is actually in line to the definition of the trig functions we have in a right triangle. Okay, so for example, the way we look at that, if this is our angle theta and this is our right triangle, then sine theta will be the opposite over hypotenuse, right? Cosine theta is the adjacent over the hypotenuse, and tangent theta is opposite over adjacent. So it actually mimic what we learned earlier in right triangle approach. Now, the thing is, once we superimpose that on coordinate system, then we allow our x and our y, then later on becomes coordinate in quadrant 2 and quadrant 3 or quadrant 4, which corresponds to a theta more than 90 degrees. Okay, now suppose for example, let P be coordinate -5, 12. Okay, and theta be the angle in standard position to OP. Okay, so pictorially it looks like this. Yeah, I'm worse than him. Okay. I was thank you, Anders. Okay, so the theta we were dealing with is this theta. Notice this theta is more than 90 degrees now. Okay, now the way we define our sine, cosine, tangent in right triangle approach will not allow us to deal with angles more than 90 degrees. Okay, now once we superimpose that on rectangular coordinate system and redefine, not changing the definition, but applying the definition in even more general situation using this here, okay, then we can see that sine theta will be the opposite, in this case the y, over the r, right? If this is the r, cosine theta equals to -5 over r, and tangent theta will be 12 over -5. Okay, now of course, to fully answer this question, we need to find this r. Can anybody tell me what r be? This is
13.
That's 13, that's right, because the length here is 5, right? And the height here, the length here is 12, so r equals to 13, that's right. Okay, so sine theta then becomes 12 over 13. Okay, cosine theta is -5 over 13, and tangent theta is -12 over 5. Okay. Now, of course, if you want to go on, just to make your life a bit harder, life is hard anyway. Okay, then what is secant theta? Secant theta is the reciprocal of cosine, that's -13 over 5. You see the way I answer my secant theta? I do it from cosine. Okay, even if you don't ask me this blue color first, let's say you ask me, Thomas, what's secant theta? I will answer it from cosine point of view first. Okay, so I will first answer cosine theta, and then from there I do the reciprocal. Okay, now cosecant theta equals to 13/12, and cotangent theta will be -5/12. Okay. Now, then using these, we are able to go on a bit further to something quite important for us to see. Notice that in quadrant 1, the coordinates are positive, positive. Therefore, you see that sine, cosine, and tangent are all positive. Okay. Imagine this, sine theta of positive over r, right? But r always positive. Cosine theta is the x over r, the x is positive, the r is positive. Likewise, tangent theta, the y is positive, the x is positive, right? So all of these will be positive. However, in quadrant 2, the x is negative while the y is positive, right? So sine in quadrant 2 will be y over r. The y is positive, the r always positive, so that will be positive. However, cosine theta, it will be x, which is negative, over r, which is always positive. So you see that in quadrant 2, only sine is positive, cosine is negative, and you will see, consequently, tangent will also be negative. Okay, well, because the tangent part is positive over negative, that's how we get that negative. Okay, so from there we see in quadrant 2, only sine positive. Of those three, sine, cosine, tangent, in quadrant 2, only sine is positive. Now, I would like you to try to do the analysis for quadrant 3 and quadrant 4. In quadrant 3, both x and y are negative. In quadrant 4, the x is positive, yet the y is negative. Let me give you 1 minute for that. Oh, thank you very much. Thank you. Wow. Yeah, the reason I asked you to memorize it this way, this thing here, okay, and explain to you using pictures, okay, okay, because I know it is true that a lot of you, including me myself, is a visual learner. Did somebody just flush the toilet? Well, anyway, don't worry about it. It's okay, totally fine. I asked you to memorize this table here, okay? And I derived the formula for 30, 60 degrees, 45 degrees, okay? Now, the reason is because I know you can memorize it that way, and you need that skill, though. Okay, you need that skill. So when I say, "Oh, don't tell me that you are a visual learner, but you cannot memorize it," it's not because I want you to eat your own word. No, that's because I know you can do it. Okay, you can do it, and because you can do it, I want you to do it. Okay? This is not too hard to memorize, but memorize it that way. Okay. So I give you the picture and the explanation of why we get this box here. I want you to memorize it. And on the top of that, why you can memorize it this way, this is the reasoning. Okay? Now, hopefully then, if somebody asks you the question, why we have that all sine, tan, cos? Oh, because from the coordinates. Okay? What it has to do with coordinates? Well, because we define sine, cosine, tangent on coordinate planes as y over r for sine, x over r for the cosine, and y over x for the tangent. See? Okay? So you kind of like put some pictures together, then you are able to memorize that better. Okay? Yeah. Thank you though for the one who reminding me about the recording. Yeah, that's very crucial. Now, with that said, then you are ready to do problems from 5.2 suggested homework. For 5.2 will be number 1 to number 0.5, and then number 29 to 33. On the other side, number 75 and 77. And now I will not ask you to prove, oh, number 87 also. I will not ask you to prove the identity yet. Okay, don't worry about it. We will do it actually next time. I need you to memorize the basic identities first. Okay, group 1, B1, B2, B3. I need you to memorize those. Okay, now with the time I have left, only 10 minutes left, let's go back to 5.1. I may actually spend so much time here unnecessarily. That's why I prefer to, you know what, I do it later. Okay, now I think with the other 9-10 minutes left, I will do this part, the radian measure. Okay, definition of radian measure. Radian. Okay, now what is radian measure? Suppose we take a look on a unit, a circle. Suppose I have a circle and we have 2 radii from the center. So think of it this way. Now this theta is in radian, and theta is defined to be the arc length over the radius. This is the radius, this is the arc length. Oh, sorry. Earlier I said that somebody's flashing, but it sounds like it's actually a traffic sound, huh? Okay, so radian, the radian measure is the arc length subtended by that angle over divided by the radius. Okay, that's radian measure. So when we say, suppose, for example, when we say theta equals to 2 radian, okay, or sometimes we just say theta equals to 2. Well, why we don't need to write the radian? Because theta, the angle in radian, is actually the ratio of 2 lengths. Okay, the ratio of 2 lengths such that the units will cancel. Okay, now when we say theta equals to 2, it means the side, I'm sorry, the arc length is 2 times the radius. So think of it this way, that if this is the radius, then and this is twice the radius, Okay, then the angle will be the central angle formed by that situation. Okay, so angle in radian again is the ratio of the arc length subtended by that central angle theta divided by the radius. Now we get used to deal with angles in degrees, and if we go to radian, of course, if this is the first time you play this way, you do this, then you may have some hard time. Don't worry, me too. When I first learned it, I have that hard time too. Okay, but having hard time doesn't mean we stop. Okay, no, I did it. A lot of people did it, and you should be able to do that too. Okay, being hard should not stop us from learning it. Okay, in fact, if everything you learn is easy, then trust me, so many people ahead of you, right? Okay, no, that's not the case. We learn hard stuff because we want to be better than other people who don't want to learn. Okay, now let's see. Then how do we relate the degree measure and the radian measure? It will be as the following. We know 360 degrees is equivalent to what radian? 2 pi radian. Oh, Thomas, how do you get that 2 pi radian? Well, because of the following. One full circle, one revolution, or one cycle. Imagine if you go one full circle. So from here, you go one full circle. Okay, then the arc length will be 2 pi r, right? Divided by r. Okay, so the theta will be 2 pi, right? Now that's how we get that one revolution angle in radian is 2 pi. Now therefore we can derive that pi is equivalent to 180 degrees. Okay, now this is super important. This is super important. This gives us the equivalence between degree and radian. Suppose I need to compute, if you give me, for example, then, suppose, for example, what is 75 degrees in radian? Then I will multiply by pi over 180 degrees. Oh, Thomas, why is that? Because I need to kill the degree and get the radian. Notice that when I multiply by pi over 180 degrees, then the degrees cancels, right? Okay, and we end up with, actually I can cancel the 75 and 182, right? Reduced by 5, let me write it down first. 75 pi over 180, reduced by 15, what will that be? 5 pi over 12. Okay, now this is now in radian. Okay, now then, suppose I have the one we have earlier. How about 2 radian? What is that in degrees? 2 radian in degrees, now that's 2 times. If I want to make it into degrees, then I multiply by 180 degrees, and then I cancel the radian. Okay, now that will give me 360 over pi degrees. Now you can use your calculator. 360 divided by pi, it gives me 114.59156 degrees.
Professor?
Yes.
Just a quick question in regards to switching degrees and radians in your calculator. For this, you would have to switch to radians?
Oh, no. If you want to compute the sine, cosine, tangent, right? You don't need to change it to degrees. You can just change the mode instead.
Oh, that's what I meant. Yeah, okay.
Yeah, okay. Yeah, you can just change the mode. But sometimes the question that have interest more is I ask you to convert the degrees to radian, radian to degree, like what I did just now.
Thank you.
Okay. Yeah, but if you want to compute, for example, if you want to compute what is sine 2, you see that I don't use degree sign, right? I use, if I don't use degree sign, then it must be in radian. Then how to compute this? Let me show you my calculator. Now, how to compute this? Then I need to first go to my mode and change it to radian. Okay, now then I compute sine 2. Like that.
Got it. Thank you.
Yeah. Instead of converting that radian into degree and then from degree you apply the sine, no need. Okay. Now we go back to my notes. Yeah. So if that's the case, then just use your calculator. I get 0.909 something earlier, as I remember. What's that? Let me see again. 30. 30. Okay, now it's 11:55. I have to stop here. From 5.1, this 5.1, what problems I need you to do? I think I assigned you some problems last time, but on the top of that, suggested homework from this 5.1b, the one I need you to do, will be number 9 to number 15. Okay, that's basically the conversion from radian to degrees and degrees to radian. On Wednesday, I will go to 5.3 first, okay? And then if I have extra time, I go back to this 5.1. Okay, again, 5.1 is not really necessary for us to move forward, but there are some application, good application problem that you will see here and also in calculus that requires you to know some background here. Okay, but for us to progress in trigonometry, we need 5.2 and 5.3. Okay, that's why I did 5.2 first. Okay, any question?
Thank you, Professor.